going to talk about an application of quantum field theory in space-time to cosmology, and actually I'm going to talk again about adiabatic regularization. So it's nice that the previous speakers has also talked about this, and in particular we're interested in the vacuum energy density. So it was Seldovich, a Russian physicist in the 60s, who first notices that naive calculations, naive predictions within quantum field theory of the zero-point energy could lead to enormous contributions of the order of m to the fourth, where m is the mass of a particle of the standard model. So this is translated to observations by saying that the observed value of the vacuum energy is almost 34 orders of magnitude bigger than for instance, the zero-point energy associated to the electron. I mean, the problem can be even bigger if one considers bigger scales, such as Planck mass, but we don't have to go that far in order to face a big problem. So some efforts to solve this problem have their own problematics. For instance, the MS scheme of normalization leads to that expression for the one loop correction to the vacuum energy density, and we end up with this expression. And if we want the left-hand side to be equal to the observed value in cosmology, we have to set these two guys here. They have to add up to a small value. I mean, this term here is of order m to the fourth, and this term here is of the order of 10 to the minus 47 JIPS to the 4 in natural units in cosmology. So we have to set this quantity with a precision that it's crazy of several decimal places. And this is what we call the fine-tuning problem. So there are other motivations to study the problem of the vacuum energy density. Another one is the so-called coincidence problem, and is the fact that the vacuum energy density at this precise moment in the expansion history is of the same order of magnitude as the energy density associated to matter. They are of the same order of magnitude just at the moment. And additionally, from the cosmological point of view, there are extra motivation from the point of view of the cosmological tensions in the H0 and sigma H parameters to search for new physics. So we have extra motivations from the point of view of phenomenology. So the goal here is to try to reformulate the previous problem in such a way that we can we can connect the problem with cosmology and its phenomenology. And just a reminder that the cosmological principle permits a vacuum energy density which evolves with time or with a dynamical variable. So what we are, let me review a little bit the running vacuum model, which is a model that has been around in the literature for some decades, and basically states that the vacuum energy density in the universe can be parameterized in that way, with the vacuum energy density, with the vacuum energy density parameterized with the Hubble function in that way, with this parameter mu, small parameter. So, this kind of models have been interested in the literature from many perspectives, but basically from general normalization group arguments and arguments of covariance. So, or even for phenomenological reasons, there is no strong grounds there. There was no a strong physical reason for justify this kind of models beyond the pure phenomenology. So what we are going, I'm going to do now is to present a calculation in QFT in order to motivate the previous model that I show you. So we are going to work in a especially simple scenario in which just one scalar field is present, one real scalar field. Just for simplicity, we are considering a semi-classical approach to the problem. I mean, we work with Einstein-Hilbert action. We include the Beer parameter, Roland, which in principle is just a Beer parameter induction, and a non-minimally coupled scalar field I mentioned to reach a scalar. So we can consider the Fourier model decomposition of the scalar field with annihilation and inclusion operators and usual commutation relations. And then the Klein-Gordon equation for the modes is translated in that way. This expression is similar to the one that Francisco has shown before. And again, we propose the WBKB method for solving this equation. I mean, this is an equation that we cannot solve analytically. We have to go for a way to solve the equation with an iterative process, which is called WBKB. And well, we propose this ansatz for the solution. And when we propose this ansatz, then this function here that I call with this capital WB has to satisfy this differential equation, where here this WB can be described in different adiabatic orders. This is the same notation, well, the same kind of language that the previous speaker have used. So just a detail here, we observe that there are only even numbers. This is because of the covariance of the theory. We only have tensors of even order. So this is translated in the expression of WBK. And we also include this arbitrary scale, this capital N, because of the arbitrariness of the process. We are able to set an off-shell scale here, replacing the mass of the scalar field. So once we do that, we produce the iterative process. We are able to obtain the expression for the small omegas here, and then we are able to compute the Fourier modes, and then we are able to go for the observables in a similar way as it was explained in previous talks. So once we have this construction, we can compute the Fourier modes. We can go for the computation of the energy momentum tensor associated to the fluctuations of the scalar field, and in particular, we can go for the 0-point energy, which is the 0-0 component of the energy momentum tensor. Of course, the energy momentum tensor has divergences. Here, I have shown a couple of them. It's working. Well, the two terms there are obviously divergent by power counting. But the normalization prescription for this energy momentum tensor is that one, we are going to subtract the value of the energy momentum tensor at the scale fixed at the mass of the scalar field minus the energy momentum tensor evaluated at the normalization scale, the arbitrary normalization scale capital M, by doing a subtraction of the first four adiabatic orders, because it is observed that in n space-time dimensions, it is sufficient to subtract the first n adiabatic orders of the expected value of the energy momentum tensor. So once we do that, the remaining integrals are perfectly convergent. This can be performed with dimensional regularization if we want to explicitize the terms. But alternative, we can see that when one writes this expression, the remaining integrals are explicitly convergent. So we don't have to deal with dimensional regularization if we don't want. So after doing that, we observe that we obtain a finite result, and the first two terms that appear in the expansion are this one and this one. Beyond that, we have terms proportional to h to the 4, where h is the Hubble function, etc. So here we have a similar expression as Here we have a similar expression to the one I presented at the beginning of the MS scheme, in the sense that we have this guy here, this n to the fourth term present, but we have not finished. We have not finished yet. This is not the vacuum energy density that we can observe in cosmology, because we have to do some work. Our definition of the vacuum energy density is actually this sum here is the sum of the bare term, or the term that we have in the action at the beginning, the rho lambda term, which now possesses a running with the scale m, plus the 0-point energy. So there are two contributions to vacuum: the rho lambda term in the action plus the 0-point energy that we have computed. And assuming a perfect fluid for this tensor here for the vacuum, we can write the vacuum energy density in that way, as the sum of rho lambda plus the 0-point energy. We should not stop here. To obtain a meaningful result that we can use in cosmology, we have to do at least two steps. The first one, consider a subtraction of scales. We have to consider the scale at an arbitrary value m and another arbitrary value m0, and do the subtraction. And when one do this calculation, I did not put it explicitly, one observes that the term, the terms m to the fourth that I finished speaking disappear. So there is an exact cancellation in the term m to the fourth, the one that is problematic, that it does not appear anymore. And after that, we have to do an extra step that consists in setting the normalization scale to a suitable energy scale characteristic for the universe. And this energy scale is, in our case, the Hubble function, because in some way it reflects the characteristic energy scale of the expanding universe. So we end up with this expression here, which is similar, that one, which is exactly the same expression that I showed you at the beginning for the running vacuum model. Here I have neglected terms beyond h to the, h squared, because, for the late stages of the universe are not relevant. Here we have computed this parameter nu effective, which can be computed from this machinery, and it contains this small ratio between the mass square of the scalar field and the Planck's mass. Some feats of models incorporating these kind of parametrizations has stated that this parameter can be as small as 10 to the minus 2, 10 to the minus 3. So, we have obtained the running vacuum law that I mentioned at the beginning. So what we observe is that the vacuum energy is not a constant. It's not a cosmological constant anymore, but has a Mill dynamics that may have potential effects in cosmology. And there is no trace of the m to the fourth terms that I mentioned before, because if one studies the beta function for the vacuum, one observes that there is no trace of this term. Additionally, during this calculation, one can calculate the running of the couplings, and the low energy regime for the gravitational constant has this logarithmic dependence, also containing this parameter nu effective. So here I have a small plot of the evolution of the energy densities in the universe for nu equal to 0.02. As we observe, there is a noticeable evolution of the vacuum energy. And let me talk just a little bit about the computation of the pressure. I mean, we can do the same analogous computation to the pressure of the energy density of the vacuum. And when one computes the pressure, one can try to compute the equation of states, the vacuum energy density. I mean, the pressure over the density, and one observes that is dynamical. It's not exactly -1 as the traditional picture of the cosmological constant. And well, one can find this evolution for this equation of state, depending on the redshift. For low redshifts, it can be approximated with this power expression in terms of the redshift. And as we see at the present, the equation of state is not exactly -1, but it can have a small shift depending on, well, positive or negative, depending on the value of the parameter. So what is curious about this expression is that if one plot it for a big range of the redshift, what one sees is that the back energy density tends to mimic the dominant component at the time. I mean, the back energy density has a equation of a state typical of the radiation during the radiation epoch. It mimics the matter during the matter-dominated epoch, and at the end, so for low redshift is when it starts to behave as dark energy, with an equation of a state below -1/3. I have more time. I just want to mention one more thing. Just let me mention that in the previous expansion, there are bigger powers of the Hubble function that I forgot about. Just let me say that they may play a role in the early universe, in the sense that they can enhance the value of the vacuum energy density in the past. So a tentative idea is to think about a possible mechanism of inflation based on these high powers of the present in the expression of the vacuum energy density. But well, for the moment, it's just a tentative idea. We have to develop more these ideas and do a more complete work on this. So just let me conclude that we have presented these computations in curved space-time, and we have been able to compute the running law for the vacuum energy density. We can extend these computations for fermions too. Well, I keep it simple for the talk, but we have repeated the computations for fermions, and the conclusions are exactly the same. And we see that the vacuum energy density does not have an equation of a state equal to -1 during all his history. It changes with redshift. Higher powers, as said, may play an important role in the universe. And well, one can study this kind of of models and related models in cosmology in order to study the cosmological tensions and feed parameters and so on. And well, that's all. Thank you for your attention.
Thank you. Any question?
Hello, thank you. Very nice presentation. I have two short questions. The first is that your results are done for a massive field. So if you have a massless field, how will it contribute to this vacuum energy? This is the first question. And the second question is if you think that this weird thing that you find can solve the Hubble tension. Like you said that it can be applied for early cosmology, but maybe it can also be relevant because I saw that a way to solve this Hubble tension is like having some phantom fluid or something like this at late times. So do you think it can be just curiosity?
Okay, for the first question, I would like to know how to do it.
Okay.
I mean, the n to the fourth term is not present for massless fields, but to be honest, we cannot naively apply this computation to a massless field.
Okay, I guess you maybe have to put a cutoff or something like this.
Yeah, it should be done in another way. It's not, at least it's not easy to adapt directly to a massless field. We should think more about how to apply this to a massless field, but at least, well, this high contribution does not appear for this. And the second question, well, in fact, we have this running law, but then the application to cosmology depends. Well, there are different models that one can construct starting from this point of view. For instance, one model that we have studied is one where we replace the Hubble function here, the h square, we replace it by the Ricci scalar, which is of the same order of magnitude during the last stages of the universe. And well, from the phenomenological point of view, well, we can just go beyond these computations. And it can potentially solve some of the tensions. In fact, we have seen some scenarios where we can alleviate the H0 tension and also the sigma tension, but well, the signal is not sufficient to claim that
Okay.
we can solve this, and also again it depends on the model you consider. So well, we have to study this more carefully.
Okay, thank you.
We have time for one question, or one single question.
Hi, thank you. For someone coming from the quantum gravity community, we usually consider the cosmological constant as a parameter of the theory that is at the same level as the Newton coupling, for example.
Okay.
And we just accept that it's just a free parameter of the theory that you will have to measure. But here you're telling me, or that's what I understand, that the cosmological constant is something that you can predict out of a calculation in quantum field theory. So is there a fundamental motivation to believe that the cosmological constant should be something that comes out of a calculation in QFT and not as just a free parameter of the theory?
Okay, thanks for the question, because I should have remarked this. This is the expression of the running law that I mentioned. This is not a prediction for the vacuum energy density. What I'm saying here, and I should have a stress, is that if you have the value of the vacuum energy density, because you have some observations, whatever, you have the value of the vacuum energy density. For instance, at the present, you are able to compute the value at another point in time, but you cannot do a prediction of the vacuum energy density. It doesn't make sense. It was pretended in the past with these kind of formulas of the MS scheme and so on. Here we have a more humble result. We are seeing that we are not able to compute from first principles the value of the vacuum energy density. What we are able to do is to predict its running once we're provided with this value, but this is totally observation.
Yeah, thank you.
Okay. I think we've finished with this session. Let's thank again the speaker and for the rest of the speakers of this session.